Alright, so today we're going to go into kind of some important theorems that make Laplace transforms a lot easier. So we had the general table of Laplace transforms back from 7.2. This is going to be kind of how can you use those in kind of a little bit easier context. So this is going to get burned into your head. Laplace transform of a function takes it from the t domain to the s domain using the following integral. Probably the most important thing and one of the most useful thing is that Laplace transforms are linear. That just makes life so much easier. It means you don't have to worry about, okay, well, I'm adding these two things together. How do I do their Laplace transform of their sum? The sum, or the Laplace transform of the sum, is the same as the sum of the Laplace transforms. It's like derivatives or integrals. Part of the reason Laplace transforms get to be linear is because they are based on integrals, which are they in themselves are linear. But there's also some additional properties that help out a lot. Like this one. If you do the Laplace transform of an exponential so Laplace transform of e to the alpha or e to the at times f of t, basically what happens is it just creates a shift of your original Laplace transform. So the Laplace transform of f of t, remember we write is f of s because we map it from the t domain to the s domain. So an exponential to and this is very specific, it's e to the at, so e to a constant times t, not e to a constant times t squared, anything like that. That will be a horizontal shift. So part of the reason, if you want to think about it, why because we've already gone through and done e to the alpha t, or e to the at. But if you think about what is the Laplace transform of 1, that's just doing this initial integral here. Integral from 0 to infinity of e to the negative st, which is where we get 1 over s. So take something like sine of 2t, which has the Laplace transform of 2 times s squared plus 4. So that means if you need to do the Laplace transform of e to the 3t times sine of 2t, well, sine of 2t is just going to be your function of t. And then notice this is kind of like your f of x plus h, if you want to go back to a Calc 1 concept or a Calc 1 thing. This is just going to be, instead of plugging it in s, you plug in s minus 3 for all of s. And that becomes this term here. So you could almost do an inverse Laplace transform just by completing the square. Because if you had something like 3 over... I'm not going to be able to pull one out of thin air that works perfectly, but you would have something like, I don't know, s squared plus, let's say it was 4t, because then I can kind of build it to make it work, and then plus 13. Then you can say, well, I can complete the square here, so I can just do 3, make this s squared plus 4t plus 4 plus 9. And then, lo and behold, this is 3 over s plus 2 squared plus 9, which throws it into that sine of 3t form. But it's now sine of 3t times e to the negative 2t, because this is minus. So you can use an algebra concept of completing the square to go backwards to find what your actual equation would be. So e to the at times any function of t is just going to be do the Laplace transform of whatever the function is, and then bring in bring in just whatever the coefficient of t was in the exponential. Makes your life a lot easier than having to go through and do basically what would turn into a pain integration by parts problem. So if you know, like for this one, you know that Laplace transform of t squared is 2 over s cubed. This is going to be, we just do this Laplace transform. This is going to be 2 over s plus 1 cubed. Because remember, it's s minus a. Our a in this case is a minus 1, so we get s minus a minus 1. Now, your Laplace transform, when we did the initial problem, we said that the Laplace transform of the derivative of a function was the s variable times the Laplace transform of the original function plus the function evaluated at 0. Well, what if you have the Laplace transform of the second derivative? Then you can kind of just expand it out. It's almost like it recursively defines itself. Because here's s squared Laplace transform of f, s f of 0, f prime of 0. And if you use mathematical induction, you could prove that the Laplace transform of the nth derivative is this sum. So s to the n, so however many derivatives you take, times the Laplace transform of the first thing, or the original function, plus you get the idea. So what does that let you do? So the Laplace transform of sine of bt is b times s squared plus b squared. So if we take the derivative of cosine of bt, we get b times cosine of bt. So we could use that theorem to actually determine what's the derivative, or what's the Laplace transform of cosine of bt. Because if we start it here, we go back to, here's cosine b times cosine of bt, which you can think this is f prime of t. Here's the Laplace transform of f of t. And then here's f of 0, which gets you that s is equal to, or that b times the Laplace transform of cosine of bt is equal to all this. Well, we don't want b times the Laplace transform of cosine of bt. We really just want cosine. So if you divide both sides by b, there you go. So with knowing the Laplace transform of sine of a constant times t, we were able to find the derivative, or the Laplace transform of cosine of bt by using the fact that b times cosine of bt is the derivative of sine of bt. So this is kind of a weird thing to think about. Where do derivatives of our Laplace transforms come into play? Well, there's a very nice theorem that says if you're doing a Laplace transform of t to the n times f, so exponential to the alpha t was a horizontal shift. Laplace transform of t to the n times a function is the nth derivative of the function's Laplace transform. So like t e to the negative t. This is t to the 1. So this means this is negative 1 to the 1. So negative gets shoved out front. Times the derivative of the Laplace transform of e to the negative t. E to the negative t, we know already that this is going to be a shift because this is 1 over, or not, it's a shift. It's a shift of 1 times, or just, it's a shift of 1 times the Laplace transform. Or not 1 times the Laplace transform, the Laplace transform of 1. And then we get that this derivative is negative s plus 1 to the negative 2. And this is just pulling in some Calc 1 principles. And we get that the Laplace transform of t e to the negative t is 1 over s squared plus 1. Which makes sense when you think about it, because this is e to the negative t. So there's our shift of 1 in there. And then if you went back and looked at how Laplace transforms of t go, it would make sense kind of looking back and forth between them. So if you want to, you can pause the video and try these and then come back and see the solutions. But I'm going to go ahead and I'll start working them. So if you want to attempt them, just pause it and give it a shot on your own. So the first thing always to do with these, again, Laplace transforms are linear. So I'm just going to do what's the Laplace transform of t squared plus the Laplace transform of e to the t times sine of 2t. From the table, the Laplace transform of t to the n is n factorial divided by s to the n plus 1. This one's just straight from the table. Nothing fancy with this one. So this is going to be, I keep drawing ones instead of 2. So 2 over s cubed. And then we have the Laplace transform of e to the t sine of 2t. So for here, our a is equal to 1. So remember, sine of 2t is going to be 2 over s squared plus 4, which means this is going to be plus 2 over s minus 1, because we have to subtract that a squared plus 4. So this one actually works out really nice. Once again, first things first, split this Laplace transform up, because the Laplace transform of a sum is just the sum of the Laplace transforms. We'll just do it this way. Now, that was bold of me to think I could write everything that's going to be on that same line. So, e to the negative t cosine of 3t. Cosine, if we go back, is s over s squared plus b squared. So this would normally be s squared over s squared plus 9, but because we have the e to the negative t, this is going to cause that shift. So this will be s plus 1 over s plus 1 squared plus 9, plus, go to the table, e to the 6t, remember this a we can think of as the shift, so this just is 1 over s minus 6, And you can think about this as just factor out the negative, and it's the Laplace transform of 1, which is just 1 over s. And you can almost think about 1 as t to the 0 and do the Laplace transform of t to the n using 0. But it's a little bit, if you can kind of see it both ways, but it's better just to go with the, you just plug in the constant and then do the integral of e to the negative st from 0 to infinity. Now, Laplace transforms are linear. This function currently is not linear. But what I can do, I could do the Laplace transform if I did square root of 1 plus, this would be 2 e to the negative t plus e to the negative 2t. And now I've taken it from nonlinear to a linear part. Or I've taken something that I couldn't break apart, but now that I've reduced it to a linear case, or expanded it to a linear case, whichever way you want to look at it, I can now do the Laplace transform of these different pieces. And just to kind of demonstrate the linearity part, I could do the integral of 2 e to the negative t, but it's better just to go ahead and factor out the 2 because it's linear, and just do the Laplace transform of e to the t, or e to the negative t, sorry. And now we're just back to Laplace transforms that either come from your table or are very common. Laplace transform of 1 is 1 over s. Laplace transform of e to the negative t would be 1 over s plus 1. Because we have the 2 out front, it's going to be 2 over s plus 1. And then finally, 1 plus s plus, or 1 over s plus 2. So if you were doing a differential equation and you ran into, after you'd done the Laplace transform, you found that it was one of, after you'd done the Laplace transform, solved for capital X or capital F, and then went through, you can see the idea of the inverse is going to come into play now of, I have these Laplace transform pieces. What did I take the Laplace transform of to get this? And this is where I talk about reading the table backwards is going to be very useful. But these are just some examples of putting those new ideas together with that original table, because the original table gives you the common ideas. This is now saying, okay, well, we can't list every possible combination, but we do have some rules to make your life a little bit easier. So we'll get to 7.4 next time, and that's where we're going to actually get into some of the inverses of Laplace transforms.